Hey guys, this is Tom. In this video I'll be addressing the second part for this course, calculating acceleration due to gravity, and how we designed an experiment to get to a final value. So, jumping straight into it, we did a bit of a brainstorm, myself and my group. There's three different methods that we came up with for calculating the gravity. One was dropping an object, one was using a pendulum, and one was using a spring. Now, if you use each of these different formulas here, you'll see that we've come up with an equivalence. So the distance of an object travelled when it's dropped equals half the accelerating force times t squared. That's from rest, hence the 0. So A being our accelerating force, G, gravity, you get this once you rearrange. The period of harmonic motion, rather, of our pendulum is dependent on the length and the gravity, so you can rearrange to get gravity is dependent on length and the period. And then last of all, the spring deflection times the spring constant over mass, because F equals ma and F equals this, gives you the acceleration. So spring wouldn't work because we have to know k to work out g, and k unfortunately is calibrated using gravity on Earth. So we get a nice little circular logic where we need to know k to know g to know k, etc. Just don't go there with the spring, basically. Pendulum, we considered it for a bit because it gives us an opportunity to measure multiple periods and then divide the total time by those periods to get the average length of one. However, we had at our disposal a high-speed camera, and that made dropping something much easier to use. So that's what we went with. Handling uncertainty, rather. The height, there's going to be an amount of uncertainty on what you're using as a ruler. So, plus or minus roughly a millimeter, plus or minus half a millimeter for the scale itself. And then you've also got the problem that you might be out, your angle might be off the perpendicular, and of course the ball's going to be falling perpendicular if you drop it. So to account for that, you have to use Pythagoras' theorem to calculate displacement sideways and how that'll affect height, or the length of a thing versus height. So basically what conclusion you end up with is that the higher a thing is off the ground, the less lateral displacement's going to affect the actual height of it. If you measure it out, say, 3 centimeters, it's going to be off by a smaller margin if it's 1 meter high as opposed to half a meter high. Next, timing. Humans are bad at timing. No way of really getting around that. The fact that we have reaction time is just not good. So, to account for that, we decided not to use humans at all and went with frames per second on a camera. So, because it's 240 frames per second, if you get the number of frames it takes for something to drop and divide it by the frame rate, so say for instance 100 frames divided by 240, you're going to get an amount of seconds. Because of that, we didn't have to worry too much about the timing. Last of all was the method of dropping it. Again, human hand, not good, because it can deflect. Say you drop it here, rolls slightly around this finger. It's still acting under the force of gravity, but at the same time, the gravity's being deflected slightly. You don't want that, so you get rid of that problem by using a retort stand and a clamp. So we did that. Having controlled for all of those different variables, we came up with a range for each of our measurements. So from 1352 millimeters high to 1353 millimeters, 0.5 millimeters high. And then same with the frames. As you can see, I've written a little bit of an explanation. Frames 125 out of 240 for seconds versus 126.5 over 240 for seconds. So the maximum force of gravity, of acceleration due to gravity we're going to record is going to be the largest distance times 2 divided by the smallest times squared. And similarly, the minimum value of gravity is going to be the smallest distance times 2 divided by the largest times squared. So the values we got for that, 9.98 meters per second and 9.73 meters per second. Because that gives us a nice range, we also want to know what the average is there. Now we can't take a straight arithmetic average because that gives us different percentages between the maximum value and the minimum value. So what you do, we take the geometric mean, which is multiplying these two together and taking the square root. That gives us this. And then taking the difference between this and each of these, you get a maximum difference of 1.3%, which is pretty good. That's basically the end of the video there. I will go on to explain a little bit more about how you calculate the point force of gravity in this case, because we are dealing with gravitational attraction between two objects, but we're discounting the mass of one of them. So in this case, the mass of the falling object, or rather the momentum of the falling object, is going to be equal to the net force multiplied by the change in time that force is acting on it. The momentum is also going to be equal to the mass times the change in velocity. That is, change in momentum, mass, change in velocity, because mass isn't changing. Force is going to be, your usual force calculation of gravitational attraction. So 6.7 e to the negative 11 multiplied by the two different masses divided by the distance between them squared. Rearranging these equations up here, you get this. Force net times the change in time is equal to the mass times the change in velocity. Because it's only moving one direction, stuff makes it a bit easier. So the net force, again rearranging this, divided by the mass is going to be equal to the change in velocity over the change in time. Now this is change in meters per second, and this is change in seconds. So meters per second gives you the acceleration. So the acceleration of a point object has to be spherical. It's important that it's spherical. It's 6.7 e to the negative 11 times the mass of the object, in this case Earth, divided by the radius, the distance, that you are above the center of that object, so the radius of the Earth. It's important to note that because we're dropping an object, it's going to fall. It's going to experience a larger force closer to the ground, but because the radius of the Earth is 6,000 k's roughly, that's 6 million meters. If you drop it by a meter, the change in this is going to be fairly small, and as a result, we get roughly 9.8 meters per second everywhere on Earth. However, another interesting point is the fact that the Earth isn't perfectly spherical. Like, it's squished through the poles, bulges at the center, at the equator, that is. Because of that, at the poles, you're closer to all of the rest of the mass of the Earth. Because you're closer to the rest of the mass on Earth, you experience a higher gravity there than you do at the equator. Similarly, at the equator, there's also centripetal motion, well, centripetal force, counteracting the force of gravity to a very small extent. However, there's also a third force involved in the fact that because the Earth is squished out via the poles, there's now a lateral component to where all of your mass is affecting you from. And so because of that, it slightly lowers the potential at the poles of gravity. So yeah, that's just an interesting point, I guess. This is how you work it out from base principles. And I'll end the video there.